Okay, so let me do one more example using the limit definition stuff for our integrals. I'm not sure that last example just went smoothly enough with all my computer issues and stuff like that and whatnot. So here's a couple of rules for sums, little formulas that you might need, because we're just going to use maybe, polynomials, this definition, linear equations, quadratic, cubic. It's one of these sum of i's, I squared, I cubed stuff. Okay, so we'll make use of these formulas when we come across an sum of I cubed, I squared, or I. These ones on the right, those are just some of the rules we got for splitting up sums. Okay, this first one, all we're saying is we can factor out constants, right? That's all we're doing there. Factor out a constant. These two are just, you can split sums up when you have sums and differences. So you can, split it up into smaller pieces or whatnot. So we're going to make use of these. All right, so let's say we want integral from 0 to 4 of x cubed plus 2x squared minus 3x dx. So the first thing is find our delta x. So the delta x is always going to be the right endpoint, or the upper bound minus the lower bound over n. So that's just going to be 4 over n. And then the x sub I, the sample points that we need, you're always just going to start off with the lower bound, or I mean the lower bound, the right endpoint or left endpoint plus whatever the delta x is times I. So we're going to have 4i over n. So that's just going to simplify to 4i over n. If we were doing the integral from 2 to 4, this would be 2 plus 4i over n. So that's going to be limit as n approaches infinity. So our little formula, remember, looks like this. So just kind of filling in the blanks. I over n cubed plus 2 times 4i over n squared minus 3 times 4i over n. And then we'll have that times the delta x, which is just 4 over n. Now, with those rules, we can always factor out anything that we're multiplying. So like the 4 over n, we can always pull that outside of the sum. Because the trick is when you have more than one kind of variable, what you want to look at is the I. That's kind of the variable as far as the sum is concerned. So as long as it doesn't involve an I, it's kind of considered a constant. So this 4 over n can be factored outside of it because it doesn't involve an I. So we're going to have 4 over n times the sum of I equals 1 to n. And I'm going to go ahead and just multiply this stuff out. So let's see, 4 cubed I think is 64, right? 4 to the third, yeah. 64 n cubed times I cubed plus, and if I square this thing, that's going to be 16, so 32i squared over n squared minus 12i over n. N approaches infinity. Okay, now I'm going to split this sum up into 3 pieces so I can do these kind of individually. So I'm just going to look at, 3 different sums here. So I'm going to have sum I equals 1 to n, 64 cubed over I cubed plus sum of I equals 1 to n, 32 for n squared times I squared minus the sum I equals 1 to n, 12 over n times I. So again, I'm just taking baby steps here. If I were working this myself, I'd probably combine a couple of these and save myself a little bit of writing. So now, again, we have this constant for the sum that I can factor out and pull in front of that little sum. I have this one I can pull in front of the sum, and that one as well. So we're going to have 64 over n cubed times the sum of I equals 1 to n of I cubed, plus 32 over n squared times sum of I equals 1 to n times I squared, minus 12 over n sum of I equals 1 to n I. Now, at this point, we could use those little formulas that I had in the very beginning. Okay, because this one, and this one are all ones I gave to you up here, right? So for the sum of I cubed, I can replace it with the n times n plus 1 over 2 squared, so forth and so on. So I'm going to make those substitutions. And I am going to need another page. All right, so here we go. Oh, stop it. Now, I cubed is n times n plus 1 over 2 squared. The sum for the I squared is n times n plus 1 times 2n plus 1. It's 2n plus 1 over 6. And then the sum for all the i's is just n times n plus 1 over 2. Okay, now simplifying a bit, I have 64 times n plus 1 squared over 2n, because what we'll see is the n squared here cancels out with one of those. Oh, that's going to be a 4n in the bottom. And then the 4 and the 64 is going to be 16. So I'm just simplifying it kind of as much as I can here. Okay. 16 plus, and then 32 times n plus 1 times 2n plus 1 over n. What I see right now is the n here, and one of those n's is going to cancel out. And then we'll have the 6, so wait a minute, 32 over 6. We'll go ahead and just reduce that. We'll get 16 over 3. Minus, and then I see this n is going to cancel out. 12 over 2 is going to give me 6. So we'll have 6 times n plus 1. Okay, so a bit of algebra there. And the limit n approaches infinity. I'm going to go ahead and multiply that 4 over n through. So 16 times n plus 1 squared over n squared plus 64 times n plus 1 times 2n plus 1, 3n squared plus 4 and 6 is 24. Okay, so notice I didn't multiply out all of the polynomials and stuff like that, but I'm just going to use our rules for our limits that we've done before. And this piece right here, you're going to wind up with n squared and blah. If you use L'Hopital's rule, that's going to approach 1. Okay. This piece here, you're going to wind up with 2n squared plus stuff, right? Blah, 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 blah. So this piece is going to approach 2/3 because you get the 2 over 3. This piece here, 1 over 1, that'll approach 1. So what we get then for this limit is 16 times 1 plus 2/3 times the 64 plus the 24. Okay, oh, sign error. This was a minus. So that was a minus. You know what? Add all those things up. We'll get 82.67. As a fraction, that would be 248/3. So there we go. Easy peasy, right? Okay, look, just be real careful with the algebra stuff and multiplying things out because it can be kind of a pain sometimes. So good luck.